as a National Historic Chemical Landmark. The Landmarks program starts at the local level of the American Chemical Society. And it was the California section that submitted the nomination leading to today's designation. We're honored to welcome representatives from the National ACS governance who are with us today, and I'd like to introduce several of those to you today. Please allow me to introduce Dr. Darrell Bush, current president of the American Chemical Society. We also have with us Dr. Attila Pavlet, president-elect of the American Chemical Society, and a member of the California section. Division 6 Director, Dr. Glenn Crosby and his wife have also joined us for this event. As well as two members of the ACS Committee on Historic Chemical Landmarks are with us, Dr. Mary Virginia Orna and Dr. Jim Long. And I have it. And also, please let me introduce, I saw her a moment ago, I hope she's here, Miss Ann Higgins from our Washington, D.C. headquarters. Is Ann and our own Mary Singleton, who's in the back here. Our past chair of the California section, and these are the two individuals who have been really key movers to make this event happen. At this time, I would like to introduce Professor Walter Loveland, who is participating in this exciting research on super heavy elements at the Lawrence Berkeley Laboratory. Professor Loveland will be our Master of Ceremonies this year, this afternoon.
I should begin by telling you, I think, that Darlene Hoffman could not be here today. Professor Hoffman, who is the Priestley Medalist of the American Chemical Society, had a family illness that took her to Oklahoma. So I know she deeply regrets the fact that she can't be here. And the time that she spent planning this occasion, I think, was extensive. It's certainly my pleasure to be able to introduce to you people who will tell you some interesting stories about the transcurium elements and their discovery here at Berkeley. I want perhaps to set the intellectual setting for this by reminding you that Berkeley has been a site for the discovery of other chemical elements. Neptunium and plutonium were discovered on the Berkeley campus along with element 85. But this occasion reflects largely the discoveries that were made on the Hill here at Berkeley and the tremendous amount of work discovering and developing the properties of the transcurium elements. As a faculty member at a university, I'm always cognizant about how research affects textbooks and how our students of today get to hear about these things. And I think it's perhaps significant to note that in a time span that corresponds to the lifetime of at least some of the members of the audience, that the periodic table of the chemical elements has changed dramatically. The periodic table of World War II is not the periodic table that we have today. This is a very different entity, and that's largely due to the work that we're commemorating and honoring here today. Certainly, no one living person has done more to alter the shape of the periodic table than the first speaker of this afternoon. And in that sense, his work, while perhaps not always mentioned in textbooks, should be. It is really the work that defines what we know about chemistry and physics and the structure of the periodic table, which really belongs on the walls of most every scientific laboratory in the world. So it's my great pleasure to introduce to you the man who has discovered more chemical elements than anyone else today, who's alive, and who has altered our perception of the periodic table significantly. Al Givarzo.
you, Walter.
Is it on?
These technical things.
Notice the theme here?
How's that? That working now? Okay, good. For a guy who's been involved in technology for the last 58 years, it's not surprising you get followed up by some little gadget. I'd like, before I start what I was going to say, I'd like to remind you of two people. One you know very well, the other you may not know as well. The first one is Mike Nitschke. Mike Nitschke was a great scientist in the laboratory. He died in 1995, I guess it was 96. And died of AIDS, among other things. But he was a fantastic person. He was the guy behind a lot of experiments. In cases, the subordinate experiment, the element 106, whose discs you see out in the lobby there, he was the guy who came up with the idea, the technology for carrying the atoms of 106 over to the wheel where they could be analyzed. And he was involved in a lot of great projects on the Hill that made a lot of difference. He's a German. He grew up here essentially, and I'm very proud of him. But he did one more thing. When he died, he made me the executive of his estate. And I discovered a small cache of money that he had forgotten about. And it was not designated to how it would be spent. And I went to various, a lot of trouble to find out how to do something with that money. It ended up with the East Bay Community Foundation. And it's that foundation that pays for a lot of things that are in the laboratory, such as awards, such as helping students on the University of California campus, such as paying for the videotape, which they're giving out to you people. We would hope that you would pay the replacement cost, so we keep handing out these tapes to students, because students are interested in this sort of thing. These are the old timers, you know, who will soon be dead, and this is what they did. Not very soon, though. I hope another couple of decades. Well, I thought maybe the thing to talk about would be something in connection with the super heavy elements, because that's obviously the big discovery of probably a long time. I think it's one of the major discoveries at the laboratory here. We're very proud of it. It involves a lot of people and a lot of technology, and a lot of good hard thinking. But the super heavies were proposed about 1964 by a couple of theoretical physicists in the laboratory here. And at first it went nowhere. No one was able to find anything, but it had to arouse the interest of people all over the world. And it started essentially a search that would go on for a long, long time, because people began to believe that these elements really did exist. I had a personal bet with Seaborg that they didn't exist at all after we tried for about 10 years and could find nothing. I bet him $100 that they would never be found. And I was very happy, would have been happy to pay off that bet, but unfortunately he escaped. But I'd like to tell you a funny story. It's absolutely true that happened along the way. This happened in 1976. I wrote it down, and to keep my failing memory accurate, I may read a portion of it. Essentially, before I start on that one, the same year, the super heavies were discovered in Nature by a team working at Florida State, a team from the University of California at Davis. I had come up with a technology for looking at very small numbers of atoms by using X-rays excited by charged particles, such as protons. And they became very good at this. And they ran into something very interesting. They could not complete it at the University of California. You say, what to Florida State? Well, they had a very fine Van de Graaff machine that was able to produce a proton beam that was very, very finely focused. So you can direct these particles to something that might be suspected of having super heavy elements. These were giant halos. Giant halos are inclusions in ores that occasionally occur in very, very tiny pieces. There are some small spheres. If you cut the sphere, section of the sphere, you'll find rings that are well defined, and you can measure the ranges of these particles that cause the coloration of these particles, of the microparticles. And they came up with the very interesting conclusion that something out there a long time ago had given them 14 MeV alpha particles. And that's strange because that was not known in nature. So they finally theorized that this was an extinct super heavy element. And the arguments were reasonably good. And finally they went to actually looking at these halos with this very fine microscope using protons. And lo and behold, they found some lines, some X-ray lines that had energies were extremely close to what they were looking for. I think it was 27,253 electron volts. And you would predict something for the element 126, only 2 electron volts away. So when they mentioned this is fantastic because they must have found the super heavy elements because this X-ray line matched what you'd expect very closely. Well, imagine the furor this caused throughout the world, essentially. I was called almost the same day when they were going to announce it. And I was sort of taken aback because today it sounded like as if they had really done it. Well, think a moment. If they had found super heavy elements in this little tiny micro halo, just a few microns in size, then it means that in the monazite ores that they got this from, there must be kilograms, maybe even tons of super heavy elements if you put them all together and looked in the right place. And this was pretty mind-boggling because think of this image. If it was really element 126, the critical mass would be much, much less than it would be for plutonium. And that means that you would be able to make micro bombs that were very, very small because it had tremendous force. And this is kind of scary because imagine India being has most of monazite sands, and if they had all the super heavy elements in the world, a good pardon, it's kind of dangerous. However, after thinking about some of the data and looking at it more closely, we began to find flaws with it. Indeed, it turned out to be wrong. When you did the analysis a different way, it was due to an impurity of praseodymium. It was excited by the protons that gave a gamma ray line that no one knew about before that just happened to be where the element 126 X-ray line would be. Well, this didn't knock down the super heavy elements entirely, it just meant that what they did was wrong. So what we decided to do, somewhat a little later, just within a few months of this, we decided that we had not found the elements in the usual way. Let's try something a little bit better. And taking all the technology we had, we decided to take curium-248, which is a heavy isotope of curium that is available in the laboratory, and bombard it with calcium-48. Calcium-48 occurs in your bones with very tiny quantities, 1 part in 2,000 or so. In order to separate it, it's cost something like $100,000 a gram, so it's kind of expensive. But we had enough of it that had been purified at Oak Ridge, and we had the super highlight. By this time we had the super highlight, the machine up.